Okay, so this is class 4. So we will continue with characterization of colloidal dispersions. We briefly started looking at how to characterize particle size and shape. I had mentioned that there are several techniques available for characterizing particles, light scattering based and microscopy based, in which we briefly discussed about dynamic light scattering, static light scattering, and in terms of microscopy there is optical microscopy, electron microscopy. So all these techniques can be used, and what you are looking at, the pictures here are cases where you have something called as a monodisperse particle. That means the particles are all of identical size, right? But that need not be the case always, because whenever you do synthesis you will always end up with something like this. You may have a distribution of sizes. This is what is called as polydisperse, right? Okay. So when you have monodisperse particles, the only parameter that you have to characterize the particles for is in terms of the physical dimension, just the size, right? If it is a spherical particles, you just say diameter of the particle or the radius of the particle, that's good enough. Okay. However, when you have polydisperse particles, so what you typically do is you kind of do something like this. Okay. So you what you are seeing is an example where what has been done is they have considered 400 spherical particles, and their size has been measured by, could be microscopy, right? So you have pictures of particles, the picture which has particles of different sizes, and then what you do is you categorize these particles into classes. Okay. This class essentially means this is a what is called a class boundary out of all the particles that I have. So I am going to put them into classes of size ranging from, in this case, 0 to 0.1 micrometer, okay, and the second class is 0.1 to 0.2, like that, right? So therefore you, out of all the sizes that you have measured, you classify them into different bins, if you want to call them as, or different classes of some size range, right? And corresponding to that class or a bin, you are going to have a average size, right? So therefore if it is 0 and 0.1 is your bin, okay, then your average size is going to be 0.05 micrometer, right? So you do that, and then of course you tabulate what is the number of particles that you have in each of these classes, okay, and I can actually get what is the fraction of total number of particles in each of these things, right? If my total number is say 400, so 3 by 400 will give you this number, okay, and of course you can look at cumulative numbers and things like that, okay. So now you will always have a question as to how many classes that I should divide the entire particle size distribution into. I think what you should do is you should not go for too fewer classes. For example, I can't have 2 classes. I can't say that, hey, look, I want to go from 0 to 0.6 micrometer is one class, and then 0.6 to 1.2 micrometer. You have, what you have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 classes, but I can't say I'll only take 2 classes, right? Because if you do that, then you're going to end up with not a good representation of the size distribution that you have, okay. On the other hand, you should also not have too many classes, because what it will do is it will increase the calculation that you're going to do, right? Is it really worth dividing them into 10 classes or maybe 20 classes or 30 classes, okay? Then you're going to end up spending a lot of time for not so much improvement in the accuracy with which you can get the size data, okay. So therefore there is an optimum number that one has to worry about, okay, that you should think a little bit when you are going to do these things, okay. And typically when you get data like this, you represent the size distribution in a what is called a histogram, okay, or a bar chart, right, and that's your first class, second class, okay. All these vertical lines that you see, these are the average size that corresponds to each of these classes. Therefore you get a distribution like this, okay. And once you have a distribution like this, so from this what you can do is I can get what is the average size, and I can also get what is the standard deviation, okay. That is the best way to represent your data when you have a polydisperse sample. And once you have, this is what is called as a discrete distribution, right? Because depending upon the number of classes I am going to have, okay, I can have a few of these bars or a large number of them, okay, that still is a discrete representation of the data that you have obtained from your image analysis, for example. So, what people do is you can actually use some continuous distribution function, something called as a normal distribution function. It is also called as a Gaussian distribution function, or what is called as a log normal distribution function, which are actually represented respectively by these three expressions, and then I can fit these known distribution function to the discrete data that you have obtained, and the more class that you are going to have, the more closer would be your discrete representation to the continuous representation that is represented by these lines. Okay. And if you have a log a normal distribution, so this f of x into dx will tell you something about what is the fraction of the particles that you have in the size range from x to x plus dx, in a particular the fraction of particles in that size range. Okay. And of course, you are going to have a maxima, right, and that basically corresponds to x bar, which is the average size of your distribution. And if it looks like a bell shaped curve, that means around the mean it is very symmetric, then you typically use this normal distribution or a Gaussian distribution. And if you have cases like this, okay, where your size data is skewed either towards the smaller size or a larger size, then you go for what is called as a log normal distribution function. Okay. And the objective of fitting these functions to the size distribution data, as I said, is to get the average size x bar and your standard deviation. Okay. So, once you have done that, you have been able to characterize your particles for the average size and the mean and the standard deviation, and there are ways by which I can calculate what is called as a polydispersity index from such x bar and sigma, and this polydispersity index typically varies from 0 to 1. More closest to 0 it is, that means it is monodisperse, the sample R, and if the values are larger, then it is polydisperse. Typically, for all practical purposes, if your polydispersity index is less than about 0.1, you can practically consider them to be monodisperse samples. Okay, that is about the characterization of the particle size. Of course, you can have particles of different shapes, right. So, what you are looking at is cases where I have some particles which looks like a peanut, right, like a dumbbell kind of a shape, or you can have something called as a spherocylinder, which is basically a cylinder with two caps, right, something called as a spherocylinder. You could have cube like particles, right, perfect cubes, okay, or you can have rod like particles, which are, in this case, this is a rod with a small kind of it's like a bullet shaped particle. Okay. So, of course, you can have particles of different shapes, and we kind of make them in our lab, but there are definitely procedures available for you to make it. What you can do in such cases is, I can of course get what is the length distribution, what is the distribution in the length of the particles, or I can get the distribution in the diameter of the particle, or you can define what is called the aspect ratio AR, which is defined as the length of the particle divided by the diameter. Okay. So, therefore, I can either characterize the particles for the length and the diameter, or for a complete characterization I would have to look at length, diameter as well as your aspect ratio. Okay. So, therefore, I can use a similar principle that I used for analyzing spherical particles, like getting the size distribution and getting fitting the distribution to a known function like Gaussian distribution or log normal distribution, and then extract the average size and the sigma. Okay. I can do a similar thing also for each of the physical dimensions for non-spherical particles. Okay. That is what you typically do. Okay. So, now that we have characterized the particles for the size and the shape, let us look at some other parameter that you can use for characterizing the particles. So, I am going to start with particle density. So, question again, so how do you characterize particles for the density? Can you think of any method? So, I will give you a sample of colloidal dispersion, and I will tell you, you go and tell me what is the density of the particle. How do you do it? Let us say that I have a container and it has particles. Okay. okay, and I have characterized these particles for size and shape is done. Now, let us look at how do we get the density. Okay. Of course, there are different methods available in the literature. I am going to tell you a method which is based on what is called as a solution densitometry, okay, in which what you do is I take my dispersion, okay, of particles, okay, I prepare a series of solutions where I have particles of different concentrations, maybe a little bit low and maybe without particles. Okay. I basically have a series of solutions, okay, or series of dispersions if you want to call them, of dispersions of particles of different concentration. Okay. Let's think a little bit on how do we from that how do we get the particle density data. So, what we will do is I am just going to rub this off quickly. Okay. Okay, let us think about so if I have a dispersion, okay, if md is the mass of the dispersion that I have, okay, I can write that as mass of the particle that I have in the dispersion plus mass of the solvent. Is that okay? Right? And this is only true if I am considering what is called as a ideal mixing, because you could have cases where I can mix two dispersions or two fluids, and I could have change in the volume as well, right, okay, or I could have change in the mass as well, right. So, therefore, what I will do is I am going to say that volume of the dispersion is equal to volume of the particle that I have in the dispersion plus volume of the solvent, right. Ideal mixing assumption, no change in the volume. So, what I will do is I will divide everything by mass of the dispersion. Okay, I am dividing the entire equation by mass of the dispersion on both the left hand side and the right hand side, and md Vd by md is equal to Vp. I am going to divide this by mass of the particle in the dispersion, multiply that by mass of the particle divided by, okay, I have md here, plus volume of the solvent divided by again mass of the solvent multiplied by mass of the solvent, again md. Is it okay? Yeah, a simple manipulation. So, this parameter, right, volume of the dispersion divided by mass of the dispersion, that is same as 1 over rho of dispersion, okay, that is the density of the dispersion, right. I have a solution, okay, I have a dispersion of particles, and I have if I have a way of measuring the density of the dispersion, that is what is your 1 over rho d is equal to, this is 1 over rho of particles, right, multiplied by mp by md. I am just going to keep it the way it is, plus this quantity is 1 over rho of solvent multiplied by, again I am going to keep ms by md. This mp by md, that is a mass of the particles in the dispersion divided by md, mass of the dispersion, I can write it as 1 over rho p into multiplied by capital X, where X is the mass fraction of particles you have in the dispersion, okay, mass fraction of particles, that is mass of particles divided by mass of the dispersion, okay, plus 1 over rho s into ms by md, it is going to be 1 minus capital X, right, which is the mass of the solvent that you have in the dispersion, because the total mass fraction is 1, therefore, the mass of the solvent is going to be 1 over 1 minus x. Therefore, I can simplify this as 1 divided by rho p into, I have rho p here and rho s here, minus 1 over rho of solvent into x plus 1 over rho s. Is that okay?
X per rho s.
What is that?
X per rho s. Sorry,
No, right? It's fine, right? So therefore, what I have ended up is a equation which says 1 over rho of d is equal to 1 over rho of particle minus 1 over rho of solvent multiplied by x plus 1 over rho of solvent. Okay. Now, what you do is we will go back to the expression, the experiment that we were saying, right. I am going to have a dispersion. I am going to prepare a series of dispersions in which I know what is the mass fraction of particles. Okay. And it is easy to find a mass fraction, right. I take a dispersion and I evaporate all the fluid and I get the mass of the particles in the dispersion, right, just by evaporating all the fluid and measuring the mass. Therefore, the difference in the weights is going to give me what is x. Okay. Therefore, if I have a series of solutions, if I were to plot what, and if I have a way of measuring density of the dispersion, that is 1 over rho d, I am able to measure that by using a densitometer, and then if I plot that as a function of x, which is the mass fraction of particles in the dispersion, I would get a straight line where the intercept is going to be 1 over rho of s and the slope is going to be 1 over rho p minus 1 over rho s. Okay. From the intercept, I know what is 1 over rho s. I can actually get 1 over rho p. From that, I can actually extract what is rho p, which is the density of the particle. Okay. This is a very simple way of preparing solutions of different concentrations and then measuring the density of the dispersion, and from that I can extract out the density of the particle. Typically, the guideline is that if you are working with dispersions, you should consider dispersions of concentration x, okay, should be less than about 0.1. Okay. Anything more than 10% do not use it. Therefore, when you do densitometry measurements, if you consider mass fraction of the particle should be less than about 10%. So, you prepare a series of solutions within that range and then measure densitometry and get your particle density. Okay. Now, it is a simple parameter, right. The density of the particle is one of the most basic parameters. It turns out that it is a very useful quantity because I can use that data also to get what is called a specific surface area, right. We define the specific surface area as the surface area of the particle divided by the mass of the particle, right. That is what we have defined, and I had said this has units of meter square per gram, right. So, therefore, if I have a spherical particle, okay, say that this spherical particle has a density, sorry, it has a size of dp, that is your diameter of the particle that you have. Therefore, your surface area is going to be 4 pi rp square, that is your radius, or pi dp square, right, that is your surface area, okay, divided by your mass of the particle. Mass of the particle is going to be density of the particle times volume of the particle, right. So, this is pi dp square divided by rho p into volume of the particle is pi by 6 dp cube, right. Okay. So, that gets cancelled, I have that also gets cancelled. Therefore, this is going to be 6 by rho p into dp. So, for a spherical particle, your specific surface area is 6 divided by rho p into dp. If I have a way of measuring size of the particle, if I have a way of measuring the density of the particle, I can actually directly get what is the specific surface area. Okay. Of course, there are other methods for measuring surface area. You would have heard of a technique called Blaine's apparatus. Have you heard of this? In which what is typically done is you basically make a bed of particles. So, if you have these particles, you make them into a powder, you make a bed of particles, and then you basically use the flow through packed bed concept, okay, to measure the particle surface area. So, we are not going to do that, but I think this is one of the simplest way of measuring the specific surface area. You measure the size of the particle and your density and the density of the particle, and then you get that. Okay. Now, the next parameter phi. Okay, we have defined this already. So, phi is defined as the volume of particles divided by volume of the dispersion, right. Okay, so, the volume of particle is going to be Vp divided by the volume of the dispersion, right. And I can convert. So, volume of the particle is going to be okay. So, therefore, your Vp is going to be mass of the particle divided by density of the particle, right. So, Vp is going to be mass of the particle divided by density of the particle multiplied by Vd. Okay. Therefore, if you have a dispersion of some concentration, you dry out all the fluid, I can measure what is the mass of the particle in the dispersion, and I have measured what is the density of the particle again by solution densitometry. And if you know the volume of the dispersion that you are using for your experiment, I can actually plug in all these numbers, I can get the mass fraction. Okay. Again, there are other ways of measuring particle volume fraction. You could think about if you have like for example, say that I have a dispersion that contains particles, right. Okay. So, if this is in a 3-dimensional volume, what you can do is I can actually get the images of this container which has these particles, and I can get image at every location. That means, I take a slice, I can get what is the basically for every slice I can actually get what is the area fraction that the particle occupies, okay. And I can basically put them together and I can construct a 3D volume. Okay. You can also do, there are techniques like that where you can do a 3D imaging of the entire dispersion, and from that you can calculate the volume fraction. But this is one of the simplest ways of doing it. All that it requires is measurement of the mass of the particle and the density of the particle, and if you know the volume of the dispersion that you are dealing with, I can get phi directly from these data. Okay.